All right. Welcome to another deep dive with us today.
Yeah.
And today,
Said about this one.
we're going to be talking about something a little different.
A little more philosophical, maybe?
Yeah, I was going to say it's definitely very philosophical.
Yeah.
But still mathematics. We're not leaving the world of math.
Absolutely.
We're going deep into the foundations of math.
Yeah.
And really looking at the idea of sets.
Yep.
And how we can think about sets in very, very different ways than what we think of when we first learn about sets
in
our math classes.
Absolutely.
And we're specifically going to be talking about constructive and intuitionistic ZF.
Right.
And our listeners actually given us a great source for this.
Yeah, a fantastic source.
It's a Stanford Encyclopedia of Philosophy entry on
set theory.
Yeah.
Constructive and intuitionistic ZF.
Yeah.
It's a great entry.
This is very dense.
It is a dense one, yeah.
But
very rich, though.
But it's full of really interesting ideas.
It is, yeah.
So our mission today is basically to unpack the core ideas of these non-classical set theories.
Right.
Really highlight how they're different from, good old ZF set theories, Zermelo Fraenkel.
Right, right.
And we're really going to be focusing on the why.
Yeah.
Why are these different? Why do these distinctions matter?
Especially for a philosophical audience.
Yes.
Right. This is where it gets really interesting. This isn't just a technical curiosity.
It's about understanding different kinds of mathematical truth.
Yes.
Different kinds of mathematical existence.
Exactly. Different epistemologies of mathematics, right?
Yeah.
Different ways of understanding what it even means to have mathematical knowledge.
Yeah. So to get started, one of the first big things, and this is where the philosophy really starts to seep in, is that both of these theories use intuitionistic logic.
Right.
And this is very different from classical logic.
Yeah, absolutely. Huge, huge departure right at the foundation.
Yes.
And so for a philosopher, this is immediately like, whoa, what's going on here?
Yeah.
So, in classical logic, we have this thing called the law of excluded middle.
Right.
And this says that for any proposition whatsoever,
it has to be either true or false.
It's either true or it's false.
Yeah.
There's no middle ground.
Yeah.
And so intuitionistic logic says, well, hold on a second.
Maybe not.
We're only going to say something is true if we have a constructive proof of it.
Right.
We're only going to say something is false if we have a constructive proof of its negation.
Yes.
And if we have neither of those things, we don't get to say either.
It might just be
undetermined.
Undetermined.
Yeah.
For now.
Yeah.
Right. Yeah.
Until we can construct a proof.
Exactly.
So the thing is, once we make this change to intuitionistic logic,
oh, man,
that really affects how we have to look at the axioms of set theory.
Because things that might have been equivalent when you were looking at them classically.
Right.
Now, with intuitionistic logic, they could be very different.
They could be very different.
So
this is where things get
really interesting.
Yeah. And this is the point, I think, for, for a philosophical listener, this is where you really start to see that there are these genuinely different foundations for mathematics, right? We're not just like playing a little game with the axioms, like, oh, what if we tweak this a little bit?
Yeah.
These are really different commitments about what counts as valid mathematical reasoning.
Yes, about what counts as a mathematical object.
Yeah. Yeah, about what exists mathematically, right?
Yeah.
So, for example, the entry points out that constructive ZF, in particular, is trying to formalize this approach to mathematics that's called Bishop-style constructive mathematics. And for Bishop, existence means constructibility.
Right, so you can't just say something exists.
Right.
You have to show how to construct it.
Right.
Yeah.
And so this has really deep philosophical ramifications for what we think we're doing when we're doing mathematics.
Yes. So once we've made that shift, we said, okay, we're going to use intuitionistic logic now.
Right.
You have to think really carefully about which axioms of set theory still make sense.
Right. It's not just a matter of taking the ZF axioms and sort of translating them.
And being like, oh, well, now they're intuitionistic.
That is intuitionistic language. No. It's a deeper issue than that.
Yeah.
And the article talks about this idea of axiomatic freedom. Right. So because we have all these different intuitionistic principles, that might all sort of correspond to the same classical principle.
Yeah. We have a lot more choices.
We've got a lot of choices.
Yeah.
And this is what the article calls axiomatic freedom.
Right.
Right.
Yeah.
There's this freedom to explore all these different options.
Yeah.
And
it makes things that were sort of lumped together.
Yeah.
Classically.
Yeah.
They become very distinct.
Yeah, exactly. Exactly.
Yeah.
So we can make finer distinctions.
Yeah. Can you give an example of?
Yeah. So like a really concrete example is the axiom of foundation.
Okay.
So in ZF, the regular ZF, the axiom of foundation says that
every non-empty set has an element.
Yeah, every non-empty set has an element that's disjoint from it. So there's no overlap.
Right.
And this seems totally innocuous, like, of course.
Yeah.
But it turns out that intuitionistically, this is problematic.
Okay. How so?
Because it can lead to constructively unacceptable instances of the excluded middle. Oh, interesting.
So this thing that we throw out
with
intuitionistic logic can sneak back in if we're not careful.
Yeah.
And so
it's like a backdoor way.
Yeah, exactly.
To get back the law of excluded middle, which we don't want.
Which we don't want.
Yeah.
So what do we do? Well, the standard thing to do is to replace foundation.
Okay.
With this thing called the schema of set induction.
Okay.
And set induction.
Set avoids that problem.
Yeah. It avoids the excluded middle problem.
Okay.
And classically, set induction and foundation.
But equivalent.
They're basically the same.
Yeah.
But intuitionistically.
Right. They're different. They're very different.
Yeah.
And
so this is just one example
of
how even just choosing the axioms becomes
a very careful,
a really delicate matter.
Yeah.
Right.
Yeah.
We have to think philosophically about what we're doing.
Yes.
And that brings us to the two big branches.
Right.
Intuitionistic ZF and constructive ZF.
IZF and CZF.
Yes. And they both start with intuitionistic logic.
Right.
But then they sort of diverge.
Yeah, they go in slightly different directions.
Yeah. So how would you characterize the difference?
So IZF is kind of like, okay, we're going to take ZF.
Yeah.
And we're going to keep as much of it as we can while still being intuitionistically acceptable. Yeah. So we modify things that are like foundation where we absolutely have to.
Right.
But we try to keep the power. We try to keep the versatility.
So it's almost like, we've made this change to the logic.
Right.
But we still want our set theory to be.
Yeah, we want to keep as much of it as we can.
Yeah, like we don't want to throw the baby out with the bathwater.
Yeah, exactly. Exactly. But then there's CZF, constructive ZF.
And this is where things
get even more interesting.
More interesting.
So not only is it using intuitionistic logic,
right,
but it's also putting further restrictions on the axioms themselves.
On the set theoretic axioms.
Yeah. And this is driven by a couple things. One is sort of the empirical observation that actually you can do a lot of mathematics with weaker principles,
right?
Especially the kind of mathematics that constructive mathematicians
like Bishop
actually do.
Right.
So that's one motivation. But the other motivation, which is even more important, I think, from a philosophical perspective, is this commitment to the principle of predicativity.
Yes. This is a big one.
This is a big one.
Yeah. But before we jump into that, the article does mention that.
Yeah.
We're talking about intuitionistic ZF and constructive ZF.
Yeah.
There is kind of a convention.
A convention.
A naming convention.
Yeah, like a terminological thing.
Yeah.
That intuitionistic is often used for impredicative theories.
Like IZF.
Like IZF.
Okay.
And constructive is often used for predicative theories.
Like CZF.
Like CZF.
Okay.
But the article is right to point out that this isn't universal.
Yes.
So you always got to be careful.
Yeah.
And older texts might use these terms differently.
Okay, so let's put a pin in predicativity for a second.
Yeah.
And just kind of note that, when you're reading about these things, be aware of
the terminology.
Terminology.
Yeah.
Okay. So now let's talk about predicativity, because this is a big
one.
Philosophical idea.
Yeah.
And
it has a really interesting history, right? It goes all the way back to Poincaré, Russell, Weil.
Yeah.
All these folks who were really concerned with the paradoxes that were popping up in set theory and logic.
Yeah. So at its core, predicativity is about
It's about how we define things.
Yeah.
How we define mathematical objects.
Yeah, and there's this worry about
circularity.
Vicious circularity.
Yeah, like defining something in terms of itself.
Yeah, or defining something in terms of a totality.
Right.
That includes it.
Right, yeah.
So the article mentions Russell's vicious circle principle.
Yes, yes. So this is a really important
What is that?
principle in the history of these ideas.
Yeah.
So Russell actually formulated this principle in a bunch of different ways.
Okay.
But one way to put it is that...
Yeah. And I'm going to try to paraphrase it.
Yeah, please do.
Whatever contains an apparent variable
Right.
must not be a possible value of that variable.
Right. So like in simpler terms, if you're defining something and you're using quantifiers, like you're saying for all sets, or there exists a set, the thing that you're defining shouldn't be one of the sets that your quantifier is ranging over.
Right. It's like
it's like a self-referential.
It's like lifting yourself up by your bootstraps.
Yeah, exactly. Exactly.
Wow.
And so that's the basic idea behind the vicious circle principle.
Okay, so we have this sort of intuitive idea of what's problematic.
Right.
But how do we formalize this?
Yeah, so the article talks about this really important work by Pfefferman and Schutt.
Okay.
And they were building on some ideas from Kreisel.
Okay.
And they basically gave a proof-theoretic analysis of predicativity.
So they're using proof theory to understand...
Yeah, to make this precise...
That's predicativity really is.
Yeah, yeah.
Okay.
So they basically use this hierarchy of logical systems to define this thing called a predicative ordinal.
Okay.
And there's a particular ordinal that's often seen as like the limit of predicativity.
Right.
And it's this ordinal called gamma naught.
Gamma naught.
Gamma naught.
Okay.
Yeah.
And this is basically saying that like if your system is predicative, it can't prove things that are stronger than this gamma naught.
Yeah, gamma naught is like
it's like a measure.
The upper bound of predicativity in this particular analysis.
Okay.
So that's kind of the classical proof theoretic view of predicativity, but there's also another a more liberal approach. Yeah.
Yeah. And this is more common in
so this is more common
constructive mathematics
in constructive foundations.
Yeah.
And it begins with folks like Lorenzen, Myhill, and Wang.
Okay.
And the idea here is that we should allow these things called inductive definitions.
Okay.
Even if they're technically impredicative.
Okay, so inductive definitions are where?
Yeah, so an inductive definition is where you
define something by saying, well, it's either this basic thing or it's something we can construct from things that we've already constructed.
Exactly. Exactly. So it's like a step-by-step process.
Yeah.
And it turns out that theories that allow for inductive definitions can often prove things that are much stronger than gamma naught.
Than this gamma naught limit.
Right.
Okay.
And so this has led to this idea of generalized predicativity.
Generalized predicativity.
Yeah.
Okay, so we have these two different conceptions.
Yeah.
Of predicativity.
Of predicativity. And so CZF is considered predicative under this broader notion.
Generalized notion.
Yeah.
Okay.
Whereas IZF
is considered impredicative.
Yeah.
Okay, so
that's a really key distinction.
This is a big philosophical difference between these theories.
It's a huge philosophical difference.
And then the article goes on to talk about how impredicativity can arise in set theory through different axioms.
Yeah, so like specific examples.
So let's start with the schema of separation.
Right.
So in ZF, the unrestricted schema of separation is very powerful.
Yeah, it's super powerful.
Right. It
says that you can take any set B, and you can form a subset of all the elements of B that satisfy some property. Phi of X.
Right, and that property can be...
the property can be anything.
Anything you can express in the language of set theory.
Yeah.
Right.
And the problem,
is that if that property involves quantifiers that range over all sets, then you can get into trouble.
Yeah.
You can get impredicativity. And
the trouble is because you're defining a set in terms of all sets.
Right. Which
could include the set itself.
Yeah, exactly.
So you're defining something in terms of a totality it belongs to.
Exactly.
So
yeah, so like an example.
Give me an example.
Yeah, like you define a set C as the set of all elements X of some set B.
Yeah.
Such that for all sets Y, some condition holds.
Okay.
Right.
Yeah.
So now C itself is one of those sets Y that your quantifier is ranging over.
Right. And so to avoid that, CZF says...
CZF puts a restriction on separation.
What does it do? It says that the quantifiers have to be bounded.
Okay, so what does it
So instead of saying for all sets Y, you have to say for all Y that are elements of some already defined set.
Oh, so you can't just talk about...
You can't just quantify over the entire universe.
You have to talk about sets within a set.
Yeah, exactly.
Okay. So you're kind of localizing.
Yeah, you're localizing
the
quantification.
Yeah.
And that's how you avoid this impredicativity.
Okay.
And the article even points out that if you add full separation to CZF, you get this theory that's as strong as second-order arithmetic.
So it gets way stronger.
Way stronger.
Yeah.
Yeah.
Okay, so that's separation.
Right.
What about the power set axiom?
The power set axiom.
This is another big one.
This is a big one?
Yeah, so in classical ZF, this says that for any set...
You can form the set.
You can form the set of all of its subsets.
Of all of its subsets?
Yeah. And this is...
And this is problematic.
Problematic from a predicative perspective.
Yeah, because again, you can imagine defining a subset of the natural numbers.
Okay.
As the set of all natural numbers that satisfies some property that involves quantifying over all subsets of the natural number.
And that could include the subset you're defining.
Exactly.
Right.
Yeah.
So
again, we've got this potential circularity.
Yeah. So the article quotes Myhill.
Yes, Myhill gives this really nice constructive critique of the power set axiom.
Yeah.
And he basically says, look, this axiom doesn't give us a constructive method for actually forming the set of all subsets. It just says, oh, it exists.
It exists.
But it doesn't tell us how to build it.
Right. So we have this axiom that's non-constructive.
Right. And Myhill's point is that we don't actually need it.
We don't need it.
For a lot of mathematics, especially if we're doing constructive mathematics.
Yeah. So he proposes an alternative.
He proposes an alternative called the exponentiation axiom.
Okay.
And this axiom says that for any two sets, A and B, the set of all functions from A to B exists.
Okay.
Now, classically, this is equivalent to the power set axiom because you can think of a subset of A as a function from A to a two-element set.
Right, like 0, 1.
Yeah, 0, 1.
But intuitionistically.
Those are different.
They're not equivalent.
Yeah.
And so
Myhill's point is that the exponentiation axiom is constructively acceptable.
Right.
Because a function is like a rule.
Right.
It's a finite thing.
Yeah.
You can give it to me.
You can actually describe how it works.
You can actually describe it, whereas a subset, especially as a subset of an infinite set, it's like, what is that? How do you give me that?
Yeah.
So this exponentiation axiom, or sometimes a strengthening of it, called subset collection, becomes a key principle in CZF.
Okay.
And it's kind of like the constructively acceptable version of the power set axiom.
Right, because it's like we said, if you add power set to CDF,
you get a much stronger theory.
It's super strong.
Yeah. So now we've talked about how CZF is making all of these changes to the axioms of ZF.
Right.
So
a philosopher might naturally ask, are we even talking about sets anymore?
Right. That's a great question.
Like, is this still set theory?
Yeah. And so the article talks about this really influential interpretation of CZF by Axel.
Okay. And he interprets it
Yeah.
in Martin-Liff type theory.
Right.
Right.
And so type theory is often seen as like a very natural foundation for constructive mathematics.
Yeah.
And so